Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is on shear stress in beams. This is a very important lecture laying out a new concept for us. Now we've been looking at shear in structure since about lecture 3. However, at that time we were looking at the average shear stress P over A. Now we're going to look and see whenever we have a transverse shear or shear applied to a section, we're going to get a moment change. And that transverse shear not only drives a downward or upward shear on the face, it also drives a shear stress between the layers. This is going to lay the groundwork. First, we're going to cover the basics of calculating shear stresses and shear flows. Then we're going to see how that is used to calculate the forces in fasteners attaching composite sections together, meaning sections made of multiple members. And then we're going to look into how that works on thin flanged members. And then we're going to look at how that plays out for calculating the shear center so we can load a beam without twisting it. These are some pivotal ideas that is critical for the structural analyst to master. So stay tuned and watch this video as many times as you need in order to master these ideas. First, if we take a look at a cantilever beam with an external point load, we know that under the action of that load, that beam is going to deflect. And so far, we've learned how to predict those deflections based on just the normal or axial load carrying capability, that bending capability for normal stresses within the section. Now, if we imagine that this cantilever beam is constructed of three 2x4s, for example, two thin strips of material, and let's say these thin strips, while they're all fixed at one end, they're not attached together. We're still going to get that same deflected picture. However, we'll find since these beams aren't attached together, they will slide. You'll notice that lower one is on a different radius of curvature than the uppermost one, which means its length is along this arc length. That length is laid along the arc length of that deflection, and the other layers, which are on a further out radius of curvature, are going to actually not reach as far as that first one. Now remember, we learned if we had a solid section, plane section remain plane, so our beam deflects like this. There's actually internal forces that make it behave like that. If we had three individual members and we bent them into the shape, we would see them sliding on each other, so we'd see discrete differences in lengths at the end of those beams as they run. The first one deflects, and then the second one slides a little bit on, the next one slides a little bit on. Now, if we had bonded these together, as we see here, or if we had fastened them together, sticking nails down through, then when it tries to slip, it can't, because that slipping action is resisted by the nails holding it together, and then we're back to plane sections remaining plane. So what we find is, just on the end of the low action of a transverse shear, which drives shear into the beam, we're going to see that that causes sliding of one member upon the other. This is a key idea that is what drives where these stresses between the layers come from. And this, so let's take a look at how we can evaluate this further. If we start off with the same cantilever beam, let's say we have a deep beam, let's say it's just a rectangular section. We have this point force, which means we have a constant shear. We have a force applied here, which means if we take a cross section anywhere, no matter where we cut it, we have the same internal shear force. We're going to use that constant. Remember, we've been using, normally in our earlier classes, we saw F was a force and sigma was a stress, but we find in aerospace, capital F is an allowable stress, lowercase f is a calculated stress, so we've been using P for forces, external forces. When we have shear forces, sometimes we use that symbol S for that shear force. But when we have internal shear forces in a beam, it's common to use V as our internal variable for internal shear, like we did when we were calculating deflection. We took the loading function W, we integrated that to the internal shear function V, we integrated that to the moment function, and so on. So focus on that. We're going to use V for that symbol. Now take a look. We have constant internal shear in the beam, and we're going to focus between two cuts, one at A and one at B. Now, although our shear force in this beam, the internal shear, is constant, our moment is building up. Right at the end of the beam, our moment is 0, P times 0, but as we move this way in the negative X direction, we're going to get more and more moment, P times 1, P times 2, and so on. If we take this little slice out of the beam, rotate it out, we can see that we not only have a downward shear, we also have a bending moment. In this case, a bending moment would be what we call a negative bending moment, compression on the bottom. That's driving tension on the uppermost fiber and compression on the lowermost. Now remember, since that first section at B is closer to the force than the section at A, that means the moment at B is smaller than the moment at A. We're getting a moment on both, and both those moments are causing stress distributions, but the stress distribution on the left is higher than the one on the right because it's further away, has a higher moment. Okay, so we're going to take a look at this little free body. Now we're going to take this slice out now. We're going to lay this out on our paper, just that slice, and we're going to look at those two distributions of stress. We can see because the force was acting down on the rightmost face, we have a shear stress acting downward. On the leftmost face, we have a shear stress acting upward. Now, we are going to, we also have our bending distribution of stress here at B and here at A. And once again, this B one is a little bigger. Now, what we're going to do is we're going to grab this little piece here and we're going to draw that. Actually, before we do that, we can take a look. This is the shear stress right along here, and this is our two stresses due to moment. That means we have a downward shear force, we have an upward shear force. That's balanced. We have a moment and a moment. If we take the moment, if we sum our moments about A, we would get the moment at B plus V times delta X minus the moment at A at 0. Or if we took the sum of moments right over here at B, we would get the moment at B plus that V times dx minus the moment at A. No matter where we sum it, we have to have equilibrium. Now what we're going to do next, let's erase all this and let's look at this one more time. What we're going to do is take this little upper piece here and we're going to redraw it over here, with only the piece of stress that acts on it up here and over there. We're going to just do that here. This is just the uppermost part of the beam. So the rest of the beam is down here. We're just focused on the upper piece. You got that? Okay, so what we see here is we have, on the right side, we had a stress distribution going from some max stress to some lower stress, depending on where we cut it. On the left side, we have a stress distribution going from some max stress to some lower distribution. Those stresses, if we multiply those by the area, whatever that area is of that upper piece, that would give us the force acting on the rightmost face. And if we multiply that stress or integrate the stress across there, we have a uniform stress and a gradient stress. If we did that on the left side, we have some equivalent force. And you'll notice, remember, the moment at B was smaller than the moment at A, which means we have an imbalance. And the place that imbalance comes out is that cut on the bottom. You'll notice, in order to get this, what we did was we cut this side of the beam, that's this cut here. We cut this side of the beam, that's this side here. And then we chopped it through here. So this distribution is from this face here. This distribution is from this face over here. And the thing that's left is this cut here is where we develop a shear stress right underneath there. Okay? So this is a key idea that we're going to need to be able to utilize. So what we have here is we have, if we sum our forces in the x direction, right, as we see here, summing our forces in the x direction, right there. So we're saying we're going to cause summing positive to the right. All forces, they have to be equal to 0. So we have this P of shear, which is just the shear stress times that dx times that width of the beam, plus the force on the right face, which is just the stress integrating that stress over its area on the right face, minus integrate that stress at A on its face, times the little increment of area has to be equal to 0. Okay, so got that? Okay, so what that means is now our stress is just MC over I. So on the B face, it's just the moment at B times the Y minus Y bar over I. And on the A face, it's the moment at A times Y minus Y bar over I. The Y here in this equation is just that identified a different way. It's the Y position pointing upward is positive from the neutral axis or the centroidal axis. So my over I is just that distance Y minus Y bar that we know we normally talk about if we define a lower section. If you're not quite sure what I'm talking about here, remember normally if we draw a section like this, we're going to call out our X here, our Y here, and what we're talking about, if we're looking at the upper segment of the beam, what we're talking about is here is the Y bar coming to there, right? And now, so the Y bar to here, Y minus Y bar, that is what we're talking about. Except in this equation, this Y, as if our Y is acting from the neutral axis. That's a little different Y than we're normally using. Okay? You got all that? All right. So actually the shear force on the bottom face plus that integral of the stress at the A at B minus the stress at A times dA. And that stress at A and B is just my over I times dA. Now if we look at this, we see that those first terms aren't changing, so we can move that integral sign straight over to the y dA. Now when we look at that, we say, oh, wait a minute, this quantity here, that is just the first moment of the area. Remember, it's our Q, capital Q. It's just the area times the Y minus Y bar, the same one that we use to find the centroid when we calculate our section properties. That's all that is. So what that means is that we can just replace that with Q. Now remember, the shear, remember if we have a force acting and we multiply it by 1 inch, that V, internal shear, whenever we have internal shear, we're changing the moment in the beam. So if the shear is acting downward, it's going to be adding moment as we move away. So downward shear force causes moment to change. Upward shear force causes moment to change. So the force times the dx, that internal shear times dx, is equal to the change in moment. So V times dx is just that m at B minus m at A. Whatever that shear is times dx, that's how that moment is going to change. Now if we're moving from B to A, that shear force times dx is just the same as that moment. So we can rewrite it this way. PS plus VDX times Q, that's the first moment of the area, divided by I. This is I of the total section. Now we got to be careful here. Remember, when we're doing bending, MC over I, what we're saying, when we say the bending stress is MC over I, I can't write with a mouse. When we say that the bending stress is MC over I like that, what that means is we're using, let me redraw this. When we say that the bending stress is MC over I, MC over I, and actually we're dealing, the C is just the Y, right? The position from the neutral axis up to the point. The moment we're talking about, in this particular case, it's a moment about the X axis. So this is a MX. And this is the bending moment of inertia about the X. So we have M times Y over I. M about the X over I about the X times that Y minus Y bar. Now when we switch that to a shear, it's the downward shear that changes the X moment. So that's a VY. VY times dx is how that moment changes. Okay? All right, now what we're going to do here is now when we solve that, we're going to find out here that we can write that dividing this by dx. P, we bring this v dx q over I to the other side. That's a minus value, but actually our dx, remember our shear is moving. V times dx gives us an increase in moment, v times dx, but actually what we have is v, and we're moving to the left. That PB that MB minus MA is moving in the negative direction, so that's a negative x. That means it's that dx is negative, so we bring that negative quantity to the right side, so that means that's just written like this. The shear force divided by dx is equal to, now remember, shear force, pounds per unit inch, is just shear flow. So what that tells us, and this is the shear force along the bottom edge, this we can write as just the shear flow, Q. Remember we call that shear flow Q? This is the shear flow acting right here along this face is VQ over I. Now remember, our shear elements, the romantic little dudes, are always mouth to mouth and toe to toe. What that means is, if we have a little shear element here, that means if we have a shear flow acting that way, this shear flow is acting this way. That's our Q, right? And that means this is balanced, so this is upwards, and this is this way. Now you'll notice though, we have a cut here, so this shear flow, Q, can exist, but up here, that's a free face, so there's no shear flow there. But remember where before we were talking about pretending we had a constant shear, in this case, we have a shear that's building up. What we're going to find out is up at the top, the shear flow is 0. At the bottom, the shear flow is increasing. So as we move down, we're going to get an increasing value of shear flow. We're going to talk about that in just a minute. An increasing value. So the shear flow is going from 0 at the top to some value down here. But at any point, like at this point, these are the same shear flow. At this point, they're the same. They're 0. But as you move downward, you get more and more until these two are the same. No matter where we cut that, we're going to have that same shear flow at any given point. Okay? We'll see that in another little slide here in a minute. So that shear flow, which is just is VQ over I. This is V in the Y direction times Q, which is the AY bar of that thing, over the IX of the entire section is our shear flow. And recalling that shear flow is just that the shear stress is just shear flow over thickness. Now in this particular case, remember we're talking about the flow on the bottom right here, the bottom of that segment, and that's acting on that width dimension B. So shear flow divided by that width dimension B. So that means our shear stress is just VQ over IB. Now we can write this as VQ over IB. We can write it as VQ over IT. We can write it as VQ over I width dimension. We could call it VQ over I surely. But that last little variable, no matter what we call it, whether it's B, which is common, T, which is common, W, less common, surely not common at all. No matter what we call it, what we're talking about is that other dimension going into the face. That shear flow is acting like this, and so we turn that into a stress by dividing by this widthwise dimension of the thing, B, which we're calling B. That is the shear stress. These are the equations for shear flow and shear stress for this element. Okay, you got that? These are two critical equations to be able to calculate VQ over I and VQ over IB, which gives us the shear flow and shear stress. When we're evaluating sections, we'll often use the shear stress. If we're trying to figure out the force between different flanges and members of the section, or fasteners and things, we'll typically use shear flow, and we'll talk more about that as we move forward. It's important that we have these ideas so far. Now, this Q dimension, what we're going to need to do is drill down on this Q. One of the most common student and industry mistakes is not being able to calculate the correct Q, the correct first moment of the area. So it's important that we understand what that means and how that works. Okay? Let's take a look at this little slide here. Once again, this is our little piece. We are focused on that upper shaded area, and this was our stress distribution on the thing. Now, if we pull out one little shear element, like one little element from along the beam, it can look like this, and blow it up. It looks like this. Now, remember, these little romantic shears, they're mouth to mouth. These two little arrows, mouth to mouth, and on the other side, toe to toe. Just imagine those little lovers are intertwined in their mouths and in their toes. That's how these always, once you get one shear flow oriented, all the rest fall into place. We've talked about this before. However, on the right face, we have a shear force acting downward, which means we have a shear flow acting downward, but the shear stress and the shear flow are growing as you move downward because we have more and more Q. Remember, we're calculating the first moment of the area of everything above. Remember how our little cross section here, what we did, we focused on this upper face right here, only part of the face from there to there and from here to here. So since and that's going to give us the shear flow right underneath here, right there. What that means is we're going to be calculating the first moment of this area right here. It's a rectangular area. And we could calculate the first moment of this area right here. It's a rectangular area. And that's going to give us the shear flow at this point here, which sets what the infinitesimal value was of the shear stress at this corner right there. So we're going from here. If we take a look at this slice, we're actually going to evaluate, looking at the end of this thing, we know the shear stress here is 0. Remember, our shear stress is VQ, or our shear flow, over I, right? Okay. At this point, what we're going to do is, if here is the centroid, the CG, at this point, and if we cut that off parallel to the CG, there's no area above this. So this Q has a 0 area. It has a large Y minus Y bar because the Y value is this dimension here. That's large, but the area past this point is 0, so the shear flow here is 0. If we come down 1 inch, then what we do is draw a horizontal line parallel to our CG, and then we shade this area. That means this area is just that width times 1 inch, and it's Y minus Y bar. That Y value we use for this, we multiply the area times this dimension. That's the Y that we use for our first moment of the area. If we want the shear down here, we're going to draw a parallel line parallel to CG, and we shade everything above it. And now it's this total dimension, this length, times this thickness, times the distance to the middle of that slice from the centroidal axis. That's how we calculate Q. So what we see is, looking at the side of this, our Q is increasing. Now, if we had the same area, actually, we'll talk about that in just a moment. We'll talk about that in just a moment. Let me erase all this ink on the slide, get rid of the pointer. And so our shear stress is going from 0 to some value at the bottom that is increasing. Our horizontal slice, you'll notice the stress along here is a constant, but the stress along this face is increasing in a parabolic fashion. This one's increasing in a parabolic fashion, and this is a constant. And that's a function of that first moment of the area and how it influences the shear stress. If we now, okay, so we're looking at the end of the thing. Let's break this up into a bunch of 1 inch pieces. Let's say we have a 4 inch piece, 1 inch, 1 inch, 1 inch, 1 inch. Let's say we're 1 inch wide. So we have a 1 inch width, and our first little element is 1 inch. If we want to calculate the shear stress 1 inch below, or the shear flow, we would take the area, we'd cut that off. Everything above that 1 inch width times the 1 inch height is the area, times the Y position from the centroidal axis, which actually in this case, if this were 4 inches tall, would be 1.5 inches up, right? Because it's 2 inches, 2 inches here, and the middle of that 1 inch piece is at 1.5 inches. So we see that right up here, our area was 0, so our stress here is 0. Our stress here is, if we take the Q of this area times its Y minus Y bar to the neutral axis, that dimension, That gives us the Q to put into our VQ over I equation. If we come down 1 more inch, you'll notice we have the same area again, but now you'll notice the distance to the centroid of that little piece is smaller. Now remember, what we're going to be getting is a parabolic distribution. If we only were increasing the area from like 1 inch of area to another inch of area to another inch of area, we would see an increase in shear stress like this. But you'll notice this first little slice is out here with a bigger Y than this second slice, which is smaller, which means we're taking this area and multiplying by a big Y, and this area and multiplying by a smaller Y, and this area, and so on, which means we're getting diminishing returns, and that's why this is parabolic. It's going to be, and then once we get down here, and remember, if we look at this section, let me draw it this way. We have this section, here's the CG, and we broke it up into 4 slices, right? So we have 1, 2, 3, 4. Now, the Y for the first one goes to right there, VQ, the Q is this area of 1 times that Y of 1. And then we have this next one, the Y to this one is just half of that width. Those are both positive because they're both above the centroidal axis. When we get to the Y of this one, it's actually negative because we're now down below. So actually that's going to decrease. We're getting an area times a negative Y, which is going to suck. So we're increasing shear flow, and then it starts sucking away, and then we come down here and it's even more negative until it's back to 0. So our distribution is going to be parabolic. Above the neutral axis, it's going to be building for a downward shear stress, and below the neutral axis, it's going to be draining. Got that? Above the neutral axis, it's going to be growing. Below the neutral axis, it's going to be draining. All right. So what that means is if we have a rectangular section, if we want the stress at point A, we're going to just calculate we're going to draw a horizontal line parallel to the CG, shade everything above that, calculate the area of that, and then multiply it by its Y position of the centroid of that from the CG, which means from the CG up to the middle of that slice, that Y times that area gives us the Q. Now, if we have a I section, the easiest way to do this is simply to shade each section separately. So we have this piece, that area, times this Y is one part of the Q, plus this area times this Y. That's the other part of the Q. This Q is the summation of those two, or the total Q is the summation of those two Qs, and that will give us the shear stress or flow right at this point A. You see that? That's how we calculate those. All right. So if we have a rectangular section, let's say we have an H dimension and a width of B, and we have a downward shear force, if we broke this up into a bunch of uniform pieces, it looks like we have a typo here. One of my students noticed this today. This dimension here, this H should go all the way down to here, and this line should end right there. This Y8 is correct, but this H should go all the way to the bottom. See that? Okay. So actually, if we look at this, we see each area, if we broke this up into all even little areas, as we move down, if we want to calculate the shear flow at the top, we know it's 0 because there's no area above it. And then if we go 1 inch down, then it's just whatever this area is times its Y. And then we go another inch down, we've added another area, the same dimension, but our Y that we multiply by is less, and so on. Until we get down below the CG and we see we have a negative Y position, so that's draining away our shear flow. This is why we get a shear flow that's parabolic for a rectangular section, going from 0 to a max value and back again for a rectangular section. The correct way to show this, if you're asked to sketch the shear flows, would be to first draw the cross section and dimension it as we see here. Draw the direction of the shear flows and put whatever or stresses and show whatever the magnitude is with appropriate sig figs. And then next to it and on its side show how the shear stress distribution changes. In this case, we're going from 0 to 0 with a parabolic distribution that reaches a maximum at the centroid. Okay? All right. If we have a I section, now remember you can kind of see this I section. Let's say we have a downward shear force on an I section. If that were the case, now we can look at two extreme cases. Let's say first we have a beam where it's this wide, one rectangular section. If that were the case, we would have the shear stress would be VQ over I width dimension, and the width dimension is this whole width here, right? And so we would get a distribution of stress that's parabolic that looks something like this. Now, if instead we had a different section that was as narrow as the web, like this, we would have basically had, now our width dimension is just that thickness of the web. So we're going to get a similar distribution. It's going to be a lot steeper because we're going to get a lot steeper distribution of stress like this. In fact, what we have is a combination because we have the I. The first little piece is pretty wide. So the shear stress buildup, let me clear this slide here. On the real section, what we're going to get is something it's trying, if the beam were this wide, it's trying to do that. It's trying to go like this. But what we find is that VQ over I width dimension, at this point, right barely above this, our width is this much. So we have a really low stress. And just below that, we have practically the same Q, because all the Q above it is about the same. But now we have a much smaller, it's like taking this piece here and just shifting it over to here with this discontinuity here. So this is how our stress distribution looks for I sections. Because we get that discontinuity, we're building up shear stress as a function of the V and the I with the Q that's accumulated. But suddenly with that Q, it's divided by a much smaller number, so we get this discontinuity, and then we continue on as if we were going about the same parabola as before. Then it drops back off and back down. Everything above the centroidal axis is building the shear. Everything below is draining it out, feeding and bleeding the shear flow in the section. We'll talk about that idea next time more, feeding and bleeding. Right now we're looking at shear stresses or shear flows when we're looking at the shear and how it reacts downward. And in a moment we'll talk about if we look at the shear for a different direction, like a sideward one. But next lecture we will deal with thin flanged members, and we're going to have to get a little more fancy with our footwork with how that shear builds up in the member. Right now we're using a simple case of just upward, downward or rightward shear flow buildup. Got that idea so far? All right, let me erase this stuff on our slide. And then we're off. So once again, we can see, now, looking back at our I section, remember now, we're going to get a shear stress that builds up. And it's kind of small at the flanges because of the big width. And then it pops up, and it's basically nearly a constant. Now the thicker this web is right here, the thicker it is, the puffier, the more parabolic this will be. And the thinner it is, the flatter it will be. If this was infinitesimally thin, this would be basically flat. And this is why often we look at, if this were thin enough, this would be so near to flat that you could just idealize it as a flat and non-changing shear flow, like the shear flow is constant. And in that case, we can actually approximate this by simply ignoring the little contribution of this upper and lower piece. So that drives us to an approximate formula like this. this V shear divided by just the area. Now there's different ways this can do in industry. We could divide it by H and the T of the web. That's commonly done. We could divide it by this H from center of the flange to center of the flange. That's commonly done. And we could do it as just the V over the total area of the section. That's commonly done. Any of those may be acceptable or encountered in industry. For our purposes in my classes, we're going to use this as the appropriate one, as the best simple approximation of that. But the only time we're going to do that is if I ask you for the approximate or average shear stress. Otherwise, I'm going to expect you to calculate all the detailed shear stresses. In order to get the shear stress distribution, we have a few calculations. We need to recognize that at the top, the shear stress has to be 0. We would then calculate the shear stress right here on the wide section to get this value. We would then change that same value by evaluating it on the narrow section, that T web, to get this value. Then we would take a Q, add the Q. That means we're going to have the Q of this upper piece plus the Q of this piece in our equation to calculate the shear flow at the centroid. And then assume this is parabolic, this is straight line, this is parabolic, and then the rest of this is just symmetric because our section is symmetric. That's how we would evaluate shear stresses. And what I would expect my students to do is to show all the values. Okay? Now what this slide does is talk about the assumptions. Our shear stress is assumed constant across the width. But the wider we get, the less true this is. We're also going to assume that the shear stress is not affected by boundaries and the shape of the boundaries. That's not true either, and it can get more violated for sections that don't have vertical boundaries. We're also going to assume that the shear stress just leaps to its new value, like that beam where it went from this wide value to a narrow value and so on. Just leaps magically to these values. This also can't be completely true, but it's close enough for government work. These are some pictures from Hibbler's book that actually show those same ideas, how the wider we get, the more our shear stress actually varies across the width, and we're going to always ignore that. And if we have an inclined boundary, our shear stress would also be off at a different angle, which we're also going to ignore in both in our classes and in all industry work. Only maybe some graduate PhD kind of level work might you dabble in things that account for that. And even after doing a huge amount of work, you're going to find it's basically you're going to have to abandon that in order to do any kind of practical analysis. All right. So let's just take a look. Let's say we want the stress at A, this point A. That means we're going to calculate the Q for everything above it. You'll notice our shear force is acting downward, Vy. That means we're going to be using Qy, which means the area of everything above it times the Y position from the centroidal axis. Since that V is in the Y direction, we're going to be calculating it's affected or offset by the bending about the other axis, about the X axis. So we're going to be using Ix. And the width dimension we need is also going to be perpendicular to that shear force. So that's going to be Bx. So for any kind of vertical force, that's the equation. If we wanted the shear stress at this point down here, if A was down lower, now we're just going to do the same thing, same equation, but now we're going to have a little different Q that we're plugging in. It's the Q of everything away from the centroid. So any point we want the shear flow or stress above the neutral axis, we're going to cut off everything above and calculate the Q. If we need the stress at any point below the neutral axis, we're going to cut it off and calculate the Q of everything below the neutral axis. Now we could actually use the Q of everything above, but remember parts of those, the parts that are above the centroidal axis are going to be positive Qs, and the parts below the neutral axis or centroidal axis are going to be negative Qs, and the positive-negative combo is going to cause most people to make a mistake. And so you want to just think of it as cutting off everything away from the centroid to calculate the Q that you're plugging into that formula. If we have a section on a side like this with a vertical shear, now in this particular case, we want the area, the shear stress at this point A, which means all we need to do is cut everything off away from the centroid beyond that point, calculate the area of that times its y position from the centroidal axis, and plug into the same equation. The width dimension, the bx here, you'll notice we only have to cut one of these flanges, so that b dimension will be that flange width here. Now this is actually a non-symmetric section, which is going to screw things up, but mostly we're going to treat that as if it were symmetric. Since this is actually axisymmetric, we will just compute it the same way. If we wanted to stress A, we would just calculate two little elements, the Q of those two elements, add them together and calculate the shear stress there. We'll talk more about thin-walled sections like that next class or next lecture. Now, in this particular case, in case E here, you'll notice there's something different. We have another H section, but now we have a shear acting to the right. That means the shear is associated with bending about the other axis. So the moment of inertia we're going to use IY. This would be Vx. We would divide that by IY. We would also need QX now. We're going to need the area times the x position from the centroidal axis. And our width dimension is now going to be perpendicular to the shear force, which is going to be that thickness dimension in the y direction, that thickness of the web like that, and so on. So this is how we'd write that stress equation now. Do you see how that works? Now this little thing, now we hardly do this. There's only a few times in industry we'll need to do this kind of thing, but let's say we have two shear forces. That Vx is going to cause shear stress, a parabolic distribution of stress from the left side of the part to the right side. And that Vy is going to cause a parabolic distribution of stress from the bottom to the top. And we could evaluate each of these separately as the VQ over I t's of each of their components. That's going to give us two components of stress. We could put those two components of stress together in a root mean squared kind of way to calculate the total shear on the part. Those are our two shear stresses, and that should be called like an X value and a Y value, and then we could put them together with a root mean squared. We're hardly ever going to do this. I may have had a problem on the homework like this. You should be aware of this, but this is rarely done. Often our aircraft parts are designed to carry like one direction of shear kind of thing, or we'll handle them separately. Now remember back in lecture 3, we also introduced the energy associated with shear stresses. We're going to actually use the exact same derivation here, but the difference is where before our shear stresses was just P over A, that average shear stress. Now what we have is a parabolic distribution of shear stress given by VQ over IB. So our energy is derived the same way, but we plug in our VQ over IB instead. We simplify that, and what we're going to take is grab a bunch of these variables and we're going to define them as KV. So with this KV, we can just look up a tabular value. That means our energy equation looks like this, and we can use these values for KV, which keeps us from having to evaluate that integral. So this gives us an approximate way to estimate our strain energy for shear forces. If we have a constant cross section with a constant shear, then this will just be the actual magnitude of that strain energy, which would be KV V squared over 2GA times L. Got that? So our next idea then, having those concepts, is to understand how forces develop in fasteners at built-up sections. Now when we do that, the key is to cut our member. For example, if we say, okay, this nail, if we want the shear force in this upper nail, we're going to use the shear flow equation Q to evaluate this. This is our equation, VQ over I. What we're going to do is our centroid of this puppy is right here. That means we're going to cut this off where the nail is attaching it, and we're going to calculate the Q of everything above or away from the neutral axis of this segment. All of that is going to cause shear flow, which feeds the nail. So that's the shear flow acting underneath that nail along here. Not only is it down the face of the section, but it's also coming out to meet that shear flow right through that cut. So if you look at that, if these nails are spaced at a certain spacing, then however much that shear flow is acting on that spacing, from, like if the fastener is here and we have a spacing, that means half of that spacing acts from one side, half from the other side. So that shear flow times the total spacing is the total force on that fastener. So we're going to calculate the shear flow first, VQ over I, and then we will multiply that shear flow times the spacing of the fasteners, lowercase s, which gives us the shear force per fastener. Now in this case over here, the second case, we'll understand this a little better after next lecture. Let's say we want to know the force in the bolt attaching that left angle. That means we're going to cut this right here. We would find the centroid. We would calculate the first moment of this. So we'd take this area of this part here times its y minus y bar, plus this little area right here times its y minus y bar, and that plug that in here with the total shear and the total moment of inertia about this centroidal x-axis. That gives us the shear flow. If we multiply by the spacing of these bolts going into the page, S, that gives us a shear force. Now, if instead we wanted to know what's the shear force on this one down here, we would instead calculate the Q of this little piece plus the Q of this little piece, which means the area times the y distance from the centroid, right? Plug all that into with the same V and the same I to get our Q on that, multiply by the spacing of these fasteners into the page, and that gives us the shear force. Okay? Now on this other one, let's say we want to know what the force is per fastener, per upper splice fastener. That means we're going to calculate the Q of this. First we need to find the centroid of the section. Let's just imagine it's there. That means for this one, that Y we're going to need for that Q calculation is from the middle of that down to here. That area times this distance goes into our Q equation. The total shear on the section over the total moment of inertia about that x centroidal axis times the Q of that little piece will give us the shear flow acting right on this line here. And if we multiply by the spacing of those fasteners going into the page, that tells us the shear force. Let's take a look at another one. Let's say we want to know what's the shear force acting on this piece. Well, we take the Q of this little rectangle plus the Q of this little rectangle plus the Q of this little rectangle. That gives us the Q. We take the total shear and the total I about the centroid. That gives us our Q. Take the spacing going into the page. That gives us our shear. If instead we wanted the force in this fastener here, we could take the Q of this rectangle, that area, times from the midplane of it to wherever the centroid is, that's our Y, over I of the section. Now, with this, while Y matters positive and negative when we're adding or subtracting from another piece, whether that shear flow is coming into the page or out of the page, we normally just ignore the sign of that. We're looking for the magnitude of the shear force in the fasteners to evaluate the strength. That's how that is done. You got that? Okay. This is another little look at that beam. If we had those nails, that first beam, if we split that upper cap off so we can see that spacing of the fasteners through the upper flange, that's that shear flow acting underneath. It's trying to slip the one piece over the other. That shear flow is acting like that, multiplied by that spacing tells how much force develops per fastener. Okay? So that is how we calculate shear stresses for shear forces. Shear flows and shear stresses based on shear forces for beams, sections, cross sections, things like this. I've got another video. You're going to watch the concepts video, which also looks at this a little bit further to make sure you understand this principle before going on to the next lecture where we look at the shear stresses and thin-walled flanges and how those feed and bleed through the section. So stay tuned.